Okay, I'll begin. Are there questions? Okay, if not, let me then begin. So today I'll start with some formal definitions and results, which will be useful. So we'll consider a linear map from some Hilbert space H1 we'll be assuming finite dimensional Hilbert spaces. So we take, say, vectors alpha, beta in H1. Okay, so they will map to some A in H2, and then beta will map to some vector B in H2. And we'll call the map an isometry. If for every pair alpha beta, the inner product between alpha and beta is the same as the inner product between A and B. Okay, so that will be the definition of what we mean by an isometry. So given this, let me describe some obvious properties of these isometries. So the first is the dimension of H1 must be less than or equal to dimension of H2. Okay, because if you take, for example, an orthonormal set of vectors, basis vectors in H1, they will have to fit into an orthonormal set of basis vectors, or orthonormal set of vectors in H2, and that can only happen if dimension of H1 is less than or equal to dimension of H2. Okay, otherwise they will not just fit inside H2. The second property is that if dimension of H1 equal to dimension of H2, well, it's not a property, it's just an observation, then the map is called unitary. Well, that's the usual definition of unitary maps. So isometry is a somewhat more general version of unitary maps, where the target may have larger dimension than from where you start. The third property, which is also obvious, is that the composition of two isometries is an isometry. And so even though this is a general definition, in what we'll study, we'll take H1 and H2 to be a collection of qubits. Which means that the basis of H1 we can take to be I1 to Ik, and the basis of H2 you can take to be, say, J1 to Jn, where Is and Js, okay, they take value from 1 to t, each of these indices. And so this H, the map then is from H to the K to H to the N. So this is our H1. So what is H? H is basically the Hilbert space of one qubit. So H, let me write it here. Hilbert space of one qubit. And so clearly K has to be less than or equal to N. Okay, so you have a condition that K is less than or equal to N, and that's the condition that the dimension of H1 is less than or equal to dimension of H2. Okay, so this is the kind of map that will be considered. So then we have this following, we can represent an element of H1 in the following way. So you have an element of H1. Will be sum over some coefficients I1 to Ik, I1 to Ik. So these are d to the k dimensional Hilbert spaces, and the other one is d to the n dimensional. An element of H2 is B I1 J1. So the isometry map, let me now write it as a matrix. So this is the, you start from there. The sum AI1 to Ik, this goes to, it's a linear map. So this will go to, let me write this, sum J1 to Jn, I1 to Ik, some matrix. Okay, so this is the coefficient mj1 to jn, I1 to Ik, ai1 to Ik, and this is the basis state that multiplies it. So this is the isometry map. So basically, it is matrix M that encodes this map. Okay, and as you can see, this is not in general square matrix. Okay, because this n, here you have a d to the n dimensional space. Here it is d to the k dimensional space. Okay. So this is a d to the n times d to the k matrix.
The second line, this is multiplied with the first, this M thing. Okay?
Yes, yes. I mean, the whole thing continues.
Okay.
And it's clear from this that if you want the norm to be preserved, okay, this is of course an orthonormal basis. Okay. So norm preservation, this condition that alpha beta is equal to AB, this basically tells us that mj1 to jn, I1 to Ik start mj1 to jn there is sum over J1 to Jn. Okay, because so if you start from a basis vector, say I1 to Ik, it gets mapped to mj1 to jn star, sorry, mj1 to jn times this element, right? Mj1 to jn, I1 to Ik times this element. And now what you are doing is that you are taking the inner product of that I1 to Ik, the original I1 to Ik state with the original L1 to Lk state. And that's given by this. Okay, and this, or if the orthonormality has to be preserved, then this has to be given by delta I1 L1 to delta Ik Lk. And in matrix form, this basically tells us that m dagger m equal to identity. And the order is important. Okay, m dagger is not identity because it's not a square matrix. So this we should keep in mind. Okay, other questions?
Dagger is also identity, but of different dimension, right?
No, dagger is not necessarily identity. This equation doesn't tell us that dagger is identity. Because the map is asymmetric, right? It's a map from the smaller Hilbert space to bigger Hilbert space.
Yeah.
Yeah. So dagger is not necessarily identity.
Okay.
So this relation is valid, right? But the opposite relation is not valid. That if you contract the I1 to Ik to L1 to Lk and keep these indices free, then it's not the delta. It's not a product of Kronecker deltas. That point should be clear. Is that okay?
Yeah, yeah.
Okay. Any other question?
Sir, one question. To compare with the notations or the language we used for the previous lectures, H1 can we think of it as the code subspace and H2 is like the larger subspace, just as an example?
No, that's an example. H1 is the logical Hilbert space and H2 will be the physical Hilbert space. That's one example. Right? But we'll make connection to what we did earlier in a few minutes. Okay, so this is just abstract definition that we are working with.
Okay.
So in terms of these matrices, we can also introduce this idea of operator pushing, which we already saw last time. And the idea is that if you have any operator, take any operator acting on H1. Let's call it O. Then M times O can be written as O prime times M, where O prime is M O M dagger. Why? Because M dagger M is identity, right? So this is obviously trivially true. Okay, we can check O prime O is M O M dagger acting on O prime M. And because M dagger M is identity, this is M times O. Okay, that's this relation. But physically, what this is saying is that if we have any operator acting on the input Hilbert space H1, then this can be represented as another operator O prime acting on the output Hilbert space. Right? That's what is the meaning of operator pushing. That you can represent an operator in H1 as an operator in H2 if the map is an isometry. Is this point clear? Okay, so now I'm going to discuss another property of isometry, which may not be so obvious. And the property is the following. Maybe I should open a new page. So let's take M J1 to Jn, I1 to Ik. This is isometry from H to the K to H to the N. Now let's define N J1 to Jn Jn plus 1, I1 to Ik minus 1 as M J1 to Jn, and then I1 Ik minus 1 Jn plus 1. And I should put 1 over square root of d. So this one defines a map from H to the K minus 1 to H to the N plus 1. Right? Because you reduce the number of input indices by 1 and increase the number of output indices by 1. Okay, but this number, as a number, this is exactly this, right? You construct this in terms of the original isometry M. So the claim is that N is an isometry. The proof is elementary, but let me give it anyway. So you have to prove that N dagger N is identity, right? So that means you have to consider N star N star J1 to Jn plus 1, I1 to Ik minus 1, and N J1 to Jn plus 1, L1 to Lk minus 1, and then you have to square summing over J1 to Jn plus 1. So now let's substitute in terms of this. So this is 1 over d times M J1 to Jn, I1 to Ik minus 1 Jn, so Jn plus 1, and M J1 to Jn, L1 to Lk minus 1, Jn plus 1. You are still summing over the same J1 to Jn plus 1. But the sum over J1 to Jn is already given by the fact that the M is an isometry, right? Because M is M dagger M is identity. So that sum you can easily perform. So you are left with 1 over d sum over Jn plus 1, and then delta I1 L1 up to delta Ik minus 1 Lk minus 1, and then you have a delta Jn plus 1 Jn plus 1. Okay. This of course is 1. Okay. So then sum over Jn plus 1 just runs over, sorry, I think I made a, yeah, runs over d values. right? Because each of these j's are 1 over d values. So this gives you 1 over d times d.
Excuse me, sir. Should we have m star for the left m in the last second?
Yes, m star. Okay, and this is exactly what you wanted to do. Is that point clear? Okay, so n is an isometry. So physically, this means that if you are given an isometry, then you can move an input leg to an output leg. Okay, and the result is still an isometry. Okay, so you just reinterpret that same set of numbers as a different kind of matrix by moving the input leg to the output leg, and that remains an isometry. You can do it multiple times, and in fact you can do it here. You move the index ik just for simplicity, but you can move any of these indices to any place inside this, right? The ordering really doesn't make a difference. So any input leg can be moved anywhere in the output leg. So this relation is again something that will be useful for us, but you just note that you have these factors of 1 over root d every time you have this kind of movement. Okay? And this basically introduces overall constant factors in various manipulations that one does with these matrices. Now, in terms of what we did last time, we can now say that perfect tensors provide isometry. So what are perfect tensors? Perfect tensors, let me remind you that if you have t I1 to I and I to n, then any balanced bipartition is a unitary matrix. Partition is bipartition gives a unitary matrix. Okay, so t I1 to, let me write this way. So if we define m I1 to in plus 1 to I to n as t I1 to I to n, then this is unitary. Unitary, of course, means it's a unitary is a special case of isometry. And now you can generate other isometries by moving any of the input legs to output leg. So the same number, same set of numbers, t I1 to I to n, we can also interpret as n I1 to in plus 1. Sorry. Yeah, in plus 1 and in plus 2 to I to n. Or we can write this as p I1 to in plus 2 and then in plus 3 to I to n. Okay. So this, for example, generates an isometry from h to the n minus 1 to h to the n plus 1. Right? This generates an isometry from h to the n minus 2 to h to the n plus 2 and so on. Okay, so this way, starting from a perfect tensor, we can construct various isometries. Are there questions? Okay, so now let me describe one claim. Okay, again, not hard to do. So claim is the tensor network code that we introduced last time. Is an isometry. And so let me remind you what the code was. Okay, so basically, I'll come back to this. Okay, let me just, okay, let me show you the figure anyway. So here is a figure. So this was we drew its dual lattice, which means that every face you think of as a vortex at the center. And then you join those vortices by links. So you take every link in this graph that you see, and the actual link is transverse to this. So it connects the two centers, okay, centers of the faces. So that describes a graph. And then on each vortex, we have 6 legs, okay, 5 that we explicitly see, okay, which are coming out, which are the 5 links that are coming out from the vortex, and the vortex itself, okay, because that's the input from the bulk. And the idea that we take a tensor, with the perfect tensor that we introduced our last time, and put on each of these vortices, and then you contract all internal links. Okay, so that's the idea. So let me write it explicitly. So the code was that if you have A1 to AN, A1 to AK, so these are the physical qubits or boundary physical qubits, okay, which sit at the boundary. These are the logical qubits. Which describe the bulk. And this was given by the product over all the vortices. That's the bulk points. So every vortex represents a bulk point. T I1 to I6, right? This is a tensor with 6 indices. And all the internal indices are contracted. So we'll indicate the proof. Again, it was implicit in what we did last time, but now I'll try to describe how the formal analysis goes. Okay. So let me remind you again, the way we draw the link is that we put these vertices, and then, okay, we call this number 0. Sorry, number 1, say, the first one, central one.
Excuse me, sir, should not the last index be I5 and then some other index?
Yes, so here I didn't distinguish between which one is bulk, which one is the link, right? The total number of index that the tensor carries is 6, right? One of these is the bulk index, which is not contracted. And the other 5 are around the links. Is that clear?
Yes, sir, clear, sir.
Yeah, I think maybe if I draw this figure and then I can remind you also. So you draw. Okay, and you can go this way. So now you start from this as 1, and then you label the points. You group the points into layers by what is called the graph distance from 1. Graph distance of a point from 1 is the minimal number of links that connects that point to 1, right? That's the definition of graph distance. So these ones are 2, for example. Okay, so these will be 2 because the graph distance is just 1. So that's the second layer. Okay, then these will be 3, right? Because anyway, I think it should be clear how to label this. Okay. It's a minimal number of links, right? That's what defines the graph distance. Okay, so now the idea is the following. One can show, in fact, you can show by inspection, but you can also try to see in general that each in a given layer, so layers are classified by graph distance. Okay, this is general property, but you can see here, for example, take 2, right? 2 gets input from 1 only, right? So only one vertex on the previous layer, right? Each of these 2s get input from 1. These 3s get input from 2 from the previous layer, right? No input from 1. Okay. 2 links connect to 3. And similarly for this and this and this. So using this, we can interpret the perfect tensor of a vortex as an isometry whose input come from the previous layers and the bulk point. Right? Because there are at most 2 inputs from previous layers, and of course there is always 1 input from the bulk, okay, because there is a bulk point, okay, which is a free index, so that also you have to think of as an input. So those this means that there is at most 3 inputs, okay? And as long as there are at most 3 inputs, it's an isometry, right? If there are exactly 3 inputs, then it's a unitary transformation. If it's less than 3, then it's isometry. So then the perfect tensor that is sitting in each point, you can think of as an isometry. And because all the internal indices are contracted, what we have, so we have a composition of many isometries. Okay, the composition comes because we are contracting the internal indices. But of course, we know that composition of isometries is an isometry. So this essentially tells us that the map from bulk to boundary is an isometry. And this, of course, also shows that you can push the operators from the bulk to the boundary. Are there questions?
Sir, one question.
Sir, should not these
Now,
distances be 0, 1, 2 rather than 1, 2, 3?
Yeah, you can call this 0, 1, 2. It's just a question of where you start leveling. Right? It's only the order that is important, right? The actual assignment of the numbers really doesn't matter. Is that okay?
Yes, sir, clear, sir.
Yes. Any other question?
Yeah, sir. In the previous class, you showed that this pushing of these bulk points to the boundary, for this, we showed that this P will be unitary, and for that we needed the fact that the code subspace was 5-dimensional because we have a pentagon tiling.
Yes.
So when we are like using other isometries, in their case the code subspace will be lower dimension. Right?
No. Here you have gone back to the usual the code that we used last time. So using qubits and 6 index, right?
Okay.
So you cannot put a tensor with more than 6 index here, right?
Okay. So that is fixed by the tiling, and then we see what.
So the point is, up to this point, we are doing things in general, right? But now we are going back to the code that we had earlier.
Okay.
Okay, so that is the qubit code. Okay, so here these are actually physical qubits.
Okay, sir. Thank you.
Okay. So now I'll try to discuss the Ryu-Takayanagi formula. Okay, at least what is known, what one can do. So let me start with this following geometry. So this is the T equal to 0 slice of ADSA. And let's say we divide the boundary into 2 parts because we have to consider entanglement, right? We call this P prime. Oops. So we call this P prime. This is a boundary segment, and this Q prime. And then we take any cut in the bulk. So on P prime, okay, we have the boundary qubits or the physical qubits. So let me draw those. Let me draw them by red circles. This is where the links end, right? You just basically the last link basically ends here. And in the bulk, so we call this region P. This region of the bulk, this region of the bulk Q. So in the bulk, you have the logical qubits. Okay, that's the vortices. So let me draw those as well. Okay, so these are the logical qubits. And this one, okay, this cut basically cuts various links. Okay, some set of links. So let me draw those. Okay, I'll draw them by this. So is this geometry clear? So if you take the figures that we had last time, what we are doing is that we are drawing a cut through the geometry. We have first assumed that there is a, we have put a cutoff so that the boundary, there is a well-defined boundary. And on the boundary, we have the physical qubits by definition. These are the places where the links intersect the boundary. Okay, the outgoing links intersect the boundary. Then we have the logical qubits that are sitting in the vortices in the interior. And then we draw a cut. The cut doesn't pass through the vortices. It avoids the vortices, so it cuts the links. So NC, let's say NC is the number of links cut by C. So this will play the role of area. This is what we will define as the area of C. Now here, of course, because we are considering ADS3, right, this geometry, area is really a length, right, and minimal area will correspond to geodesic. Okay, but let's call this the area of C. Okay, it will be an area if it was you are considering ADS4. Okay, but in ADS3 area is replaced by length. So in the Ryu-Takayanagi formula, this NC will play a role. Okay, so now let me give some labels. So we label by A. So A is an index. This is not a qubit index. Okay, this is basically the full Hilbert space index. Okay. So this labels the basis of bulk qubits in P. So basically the number of indices that the number of values that A takes is 2 to the number of points that P has. Similarly, the index B will label the basis of bulk qubits Q. Then you have to introduce a basis for the boundary. So let me do that here. Those will denote by small a. So this is the basis these labels And then B, we label the basis of inverse space of qubits in P prime, in Q prime. Okay, I hope this is clear. Right? So A labels the 2 to the these many power of states, okay, these many power of basis vectors, and B labels 2 to the these many powers of basis vectors. A labels 2 to the these many powers of basis vectors, and then B labels 2 to the these many powers of basis vectors. And finally, I will label the qubits Hilbert space qubits on links cut by C. That's 2 to the NC damage. Okay. Okay, now I'm going to introduce some matrices. So we take okay, so these are all the definitions. We have further definitions. Okay, so take contracted. Okay, that means all internal links are contracted. Product of the perfect tensors inside okay, we take inside P first. Okay. That means P has many perfect tensors inside, right? One associated with every bulk vertex. Okay. All internal links are contracted. Okay. So what are the free indices? Okay. The free indices will be, let me write this matrix. The free indices will be I, right? Because these are free indices. These links are not contracted or anything. Okay, these are free. So MI. The bulk indices are free. Okay, these are not contracted or anything. So let's call this A. And the boundary indices, okay, are also free. That's A. So inside P it's MIAA, and inside Q, we could do the same thing. Inside Q, that we call NI. Okay, I is of course common because C is common between the two. Then B and B. These are definitions. Okay, we take the product of perfect tensors and just contract the indices. Is this clear?
Sir, why link indexing? Why coming in? Earlier we saw only the logical qubits and boundary qubits came, right? It's in the index of n.
Yes, but I mean, if I define it this way, right?
Yeah.
See, I have the perfect tensors at every vertex.
Right, right.
I can take the product and I can decide that I'll keep the index I free. Right?
Okay.
Eventually, if you want to
So
construct map from the bulk to boundary, then of course index I will be contracted.
Right.
But given a cut, I can always define the product of tensors with keeping the index I free.
Okay.
Right? These are the definitions.
So I denotes that link on which that vertex is situated. Right? Is it?
I denotes no, not on the vertex. I denotes the qubits on the links,
Oh, qubit on the link. Okay.
because
Yeah, right,
cut some links, right?
right.
So each of those links carry a qubit, right?
Yeah.
Because remember that let me go back to this diagram. So the perfect tensor that is sitting here, right? What are the indices? One index is coming from the bulk.
Right.
The other indices are coming from these links, right?
Yes. Oh, okay.
So for example, if the cut is, suppose the cut is passing through this, right? Suppose this is a cut, then these link indices I'm keeping free. Okay, I contract all the links in the interior, but these link indices I'm going to keep free and define this tensor M as a function of those indices and the bulk indices and the boundary indices.
Okay.
So this should be clear what we are defining here, right? Because since I have the product, I could keep every index free, right? And define
Right.
some quantity.
Yeah.
It's not just very useful, right? But this quantity will be useful. Okay? Where I keep the indices on the cut free, okay, and contract all the indices in the interior of P and in the interior of P.
Okay.
So the original code, right, which is this. Okay, this is the complete set of bulk indices. This is a complete set of boundary indices. This, of course, is given by summing over this index I, right? Because these indices also have to be contracted times M I A N I B. Is clear? Then the original code included that you take the product of all the tensors and contract all the interior indices, right? Now inside M and N, you have already contracted all the indices inside P and inside Q. So when you take the product of M and N, right, the only index that you are still to contract are these indices I, and that's what I have written there.
Excuse me, sir.
Yes, go ahead, please.
Not one of them be complex conjugated because we are taking inner product of two vectors, state and bra.
Yeah, okay. So let's not worry about this. Indeed, one of these indices will be complex conjugated. Well, no, maybe I should say this way. That the way you are thinking of, you are just transferring the input to output, right? So that's part of the definition of these matrices.
Okay, sir.
So M, I, A, we have to think of I and A as input and A as output, right? That's the way I'm defining it. Is this point clear?
Yes, sir. Yes, sir.
Because this also, you remember, right? The way we define this inner product is just by taking the product of perfect tensors, right? And assigning A and B as the indices lying here and A and B as the indices lying in the bulk, right? There we didn't try to complex conjugate any tensor, right? And the same procedure you are following here. So this is just a definition of this matrix. Okay, now we consider a bulk state that is factorized. Okay, later on we'll take entangled bulk state. But right now I take the bulk state to be sum over, write it there. Okay, so it takes some state inside the bulk P and some state inside the bulk Q, and then take the product. Okay, no entanglement in the bulk, no entanglement among the logical degrees of freedom. Okay, as I said, I later on will relax this assumption. And now ask, what does it map to in the boundary? Okay, that will be given by this. So this will be mapped to okay, because this inner product is basically telling us how the bulk states are mapped to the boundary state, right? So this, since the bulk state is PAPB times AB, you take the inner product with a basis vector in the boundary, yeah, and then multiply by the same basis vector. That's the way we construct the boundary state of the boundary.
So one of them should be QB, right?
Pardon? Yeah,
One of them should be QB, right? P and Q.
Yeah, thank you. PAQB. So now we are going to use this formula for this inner product in terms of the M and N matrices. Okay, this one. I wrote it the other way, right? So this I can write sum over I, then sum over A times A I just rearrange the sum. Okay, the same sum I have just rearranged. But now you see that these two factorize for a given I. This one I define as Pi up to this point. And this one I define as Qi. Okay. because this part doesn't depend on B at all. Okay, so this is a state on the so this is the basis the basis elements here are A, right? So Pi is a state in the boundary, okay, but supported only on this. Okay. And Qi is a state that is supported on this Hilbert space. Okay, that's their product. Okay, so Pi is supported on this Hilbert space, Qi is some state in this Hilbert space. So I write it once more. Sum over I, Pi, Qi. Is this okay? So this is the representation on the boundary of the state, this state in the bulk. Okay, so this, if you have a logical state, then its map to the physical Hilbert space is given here. Okay, it should be kept in mind that this is actually a boundary, state on the boundary, right? Physical Hilbert space, because it's given as a linear combination of the basis vectors A. And similarly, this is also supported in the physical Hilbert space because this is given as a linear combination of the basis vectors B. Are there any questions?
So here the level I of Pi and Qi, what do they imply? Finally, everything is summed over, but when you're leveling P by I and you're saying because I is on the in the bulk, right? The link point.
Yeah, yeah. So I is here. I is these indices.
Right.
So I labels these in. These are the basis states here. But the basis
But
states
it
don't have.
describes the state.
See, I is just counted as an index, right? But the basis states themselves don't enter, right? This is a matrix element. I to begin with was labeling the Hilbert space that was supported on this this one, right?
Yeah, right.
But MIAA, this is just a matrix element, right? Here you don't see the states I.
Right.
So the important point is that sum runs over these 2 to the NC number of independent states. So I takes 2 to the NC values, right?
Right.
Okay, but the PIs and QIs are states that are on the boundary Hilbert space, even though they are labeled by this index.
Okay. So it's like the boundary state we are representing in terms of some basis states for the link.
No, it's not. These are not basis states on a link, because these are all linear combinations of the boundary basis states, right?
Right. The state is of the boundary state, but
so the index refers to the basis states of the link. Index I, right? But that's not the same as the state I, right? Which would have been the state that is on the qubit on the link.
okay. So you're using the basis states on the links to write the boundary state.
No, because basis states on the link we have taken matrix element already, right? Because these are just numbers. Here you don't see the basis states on the link. These MIAA, these are just numbers, right?
Okay.
See, I introduced these, but I didn't. These states never entered explicitly, right? These states I didn't introduce explicitly. Okay,
Right.
implicitly these entered because these you can think of as the matrix elements.
Okay.
Or yeah, but at this stage these states haven't entered anywhere, right? Eventually these will play some role, as we will see, but so far these are just labels.
Okay.
Excuse me, sir, some clarification. Are these summation infinite? Because is it true that index I takes infinite value because there will be infinite cut over this curve C since the space is infinite?
Yeah. So the point is we are always thinking of a finite cutoff, right? And then everything is finite. See, eventually, if you want to take the limit of these two infinite cutoff, right? Infinite number of lattice points, then everything is infinite, right? A and B run over infinite set of values, capital A, capital B run over infinite set of values, and of course the sum over I also runs over infinite set of values. But once you have chosen a cutoff, right? The cutoff is basically about the where you cut off the boundary, right? How you define the boundary. We're assuming that we take the boundary to be far enough away so that you have a large number of bulk points inside, and as a result also large number of links on that cut the boundary, okay, which give the boundary points, but it's a finite number. And in that case, the C, the sum over I is also a finite sum. Is this clear?
Yes, sir, yes.
Any other question? So let me write again. So the representation of A times sum over A times sum over B Now let me remind you what the Ryu-Takayanagi formula is supposed to be for. So the RT formula is supposed to be measuring the entanglement entropy of certain region on the boundary, which means that you would have to define a density matrix by tracing out the rest of the region. So you are going to trace out the degrees of freedom associated with Q prime, which means you basically have to trace out the over the basis states B, okay, the small b, basis states labeled by the small b. Where is small b? Yeah, here. And write a density matrix for the states that are supported on which carries this index A. So let's do that. So rho of the region P prime. So now remember that Pi, this is supported on the basis states A. This is supported on the basis states. Sorry, I start. This is Qi. So rho of P prime. So you're basically trying to trace out these states, right? Because these are supported on the basis states B, these are supported on the basis states A. So this will be given by sum over Ij. Okay, this is what comes out of tracing over the basis states B. So this is a density matrix that is supported in on the basis states A, right? Because P is a linear combination of the basis states A. Is this clear? So, and now the entropy, entanglement entropy is, okay, I should have said that all this is actually, this is proportional to this, okay, because these are not normalized states. Okay, why are they not normalized? Because as we discussed, that we are thinking of these M's as matrix contractions, but in general, if you want to think of this as isometries, then you have to turn the indices. Okay, so typically, okay, the P's and these states that we'll get. Okay, let me be more specific. Okay, so this quantity that we have defined defines an isometry up to normalization, overall normalization, right? Because this one is just a contraction of all the tensors, but it's a unitary matrix if the number of, if each of these has equal number of inputs and outputs. But some of these tensors, okay, have say less input and more output, right? Say 2 inputs and 4 outputs. So in that case, you have to divide by this 1/4, okay, or oh, sorry, 1 over square root of 2 times square root of 2 to make this into a isometry. Okay, that is that 1 over square root of d factor that you saw, and those are not included here. So because of this, this relation is true only up to an overall proportionality constant. So let me maybe write it that way. So this is really proportional to this. So all the further formulae should be really thought of as being proportional. They're all up to this constant. Okay, so it's proportional to this.
So
Yes.
here instead of writing this sigma j bra qj, we should be writing b, right? Small b.
Yeah, but the point is that, so if we take qj b bqi, right? That's the same as qj qi, because qj is a linear combination of the states on B.
Oh,
Is this okay? See, okay,
yeah.
yeah. If you let me write it this way, maybe if you want to do it. Something gone wrong with this. Okay, so the point is that this one I can write sum over I pi, and then sum over b b bqi, right? Okay, then I have to take the trace over b, right? So let's try to do this. So you have sum over I pi, this bqi is just a number, and then let me write sum over j. and then sum over B prime. This is okay.
There is a cat extra, like
So this is fine. Now I have to bring this B prime here, right?
yeah,
And take the trace. Because you are trying to trace out the B, right?
yeah,
So you have to bring this one here. Okay. So that one gives a delta B prime B. Right? Because B is an orthonormal basis. So what we will get is QJB. So B prime has been set equal to B. And then BQI, sum over B. That is QJQI. Okay, that's what you see here. And then this is PI and PJ. This is over A, right? So we are not doing anything here.
yeah,
Is this okay? Right. So this is the kit. Okay. This is the corresponding bra. Okay. Now, for as far as the part of the state over Q prime is concerned, right? You have to take the trace. So I bring the this kit, sorry, this bra here, right? And take the inner product. Okay, so that gives you delta B prime. So B prime is set equal to B. We are getting this sum. Okay, and that's what we replace it by QJQI.
yeah.
Okay. Any other question?
Excuse me, sir. This ket QI are states on boundary. So is it true that bra QJ with ket QI is proportional to delta IJ?
No, it's not true in general, right? Because these are not orthonormal bases. Remember how these are defined? Let me go back. Okay. So this is the definition of PI, right?
Yes, sir.
So in general, the PI, PJ or QI, QJ are not orthonormal bases. Now they don't have orthonormal properties. Okay, that's important to remember, and this will play an important role in what you are going to do. Any other question? Okay, so let me write this formula again. So rho of P prime sum over I J I J so I and J run over 2 to the NC levels, right? Because the I and J are the indices that level the Hilbert space of the links that are cut. Okay, even though those basis states have not entered anywhere. So this means that the rank of rho is less than or equal to, again, is proportional to, is less than or equal to 2 to the NC. Okay. And this has a simple consequence that S of rho is less than or equal to log of rank of rho. And that's NC log 2. So that tells us this, you remember, is area. Okay, so this is an elementary proof. Basically, if you think of rho, okay, if you look at the diagonal form, right? Think of rho as say rho 1 to rho r, and rest are 0. Okay, because r is a rank. Then and then sum over rho I is equal to 1, right? That's the trace rho equal to 1 condition. Then S of rho, which is minus trace of rho log rho, which is minus sum over I, rho I log rho I. This is maximized when rho I equal to 1 over r. Each of the rho i's is 1 over r. And in that case, this becomes S of rho. It becomes minus 1 over r log 1 over r. And then, of course, times r, because there are r of them. That's log r. And this is the bound. Okay, the log of rank, and that's what this bound is about. Okay, so this will also play an important role. Okay, there is a bound on S, which is given by NC log 2, and the bound is saturated when rho is rho has all eigenvalues the same. So let me write it again. S of rho is less than or equal to NC log 2. Now remember that this is, we interpreted as the area of C. And this one, we are going to interpret for this problem as the analog of 1 over 4gn. This is just some constant. So is 4gn, 1 over 4gn. Okay. So if you think of this, then you see that this gives at least some hint of the Ryu-Takayanagi kind of formula, that S of rho is less than or equal to A over 4gn. Area of the cut over 4gn. Which is good because Ryu-Takayanagi formula is supposed to be that S of rho is equal to A over 4gn for the minimal area cut. Okay. Here C was any cut. But this also immediately tells us the following, that if C naught is the cut with minimal area, that means it cuts the minimal number of links, minimal area. With boundaries fixed. Fixed at the boundaries of P prime or Q prime, the boundaries of P prime. Okay, which basically means that if you go back to this diagram, okay, we keep these points fixed, okay, and we draw all possible cuts, okay, and see which one has minimal area. The one which has minimal area will produce minimal entanglement entropy, okay, because you are of course considering a so the bulk state, corresponding bulk state will be a product state again between the two sides of the cut, okay, and then the corresponding area, okay, the minimal area will provide an upper bound to the entanglement entropy of P prime. then S of rho is less than or equal to n C naught log 2, which is you can interpret as AC naught over 4 here. So this is a version of Ryu-Takayanagi formula which is immediately provable. Okay. Namely that the Ryu-Takayanagi formula at least provides an upper bound to the entanglement entropy of this region. And now we have to do some work to figure out what it will take to make this into an equality.
Sir,
Go ahead.
hello? Yeah, we could have made multiple choices of lengths with the same amount of length, right?
Multiple choices of
We are choosing one length and we are choosing that length which has the minimum length. But that need not be unique in any way. Is that unique?
the one with minimal length.
Yeah.
Yeah, that need not be unique, but the bound still holds, right?
Yeah, the bound holds. So those multiple choices of lengths with the same length, will they? Do they correspond to anything?
Yeah, right now, no. Right. Later on, we'll see what what role the links play. Right now, the links haven't played very much role, right? Except as labels of these indices. But eventually, they will play some role. Okay. In particular, when we try to decide what it takes to make this into an equality.
Okay, but this leverage was not there in the continuum case when we were considering ADA-CFT correspondence.
Well, even then,
we only chose.
See, even then it could have been that there are more than one in a complicated geometry. In ADS, this problem was not there. But in a complicated geometry, right, with the same asymptotic ADS, but maybe some inside, say, there's a black hole or there is something else, okay, then it could be that there are two surfaces with the same area.
Yeah, but in that case, those two surfaces would not have corresponded to something about this formula. We are relating the entanglement entropy with the area of this surface. And
yes,
as long as two different surfaces have the same area, they are not giving us any more information.
No, they are not giving us any more information because at least as far as the formula is concerned, right? Then if we understand what actual physical role those surfaces play, then they may give some additional information. But right now they are not giving any more information. Just from the Ryu-Takayanagi formula itself, we don't see any more information because this is just a number, right?
Yes.
Yeah. But later on, we'll see that these surfaces will at least play some role. Okay. In fact, maybe today itself, I'll discuss that. Okay, what role these surfaces could play.
Yeah.
Okay. Are there other questions? Is it clear? So let me write the formula for rho again. So rho is sum over ij pi ej qj qi, and it's proportional. And this inequality S of rho this is saturated if rho has all eigenvalues same. that basically means that rho is proportional to the identity matrix inside the subspace. Okay, of course, it has 0 eigenvalues, right? So it's proportional identity matrix, and then the rest are 0. Now this can be achieved. If the following conditions hold: Pij is proportional to delta ij, and Qi Qj proportional to delta ij. Because in that case, right, this is an orthonormal basis. And if this is delta ij, then rho becomes proportional to sum over I, pi, right? And this is an orthonormal basis. So this is clearly has all the same eigenvalues. It's basically proportional to identity matrix inside the subspace, inside the 2 to the nth dimensional subspace. Okay. So if these conditions hold, then you actually saturate the bound. Is this clear? Because see, to prove the RT formula, right, you have to try to saturate the bound, right? It's not enough. RT formula is not an inequality, it's an equality. Okay. So to prove the RT formula, you have to actually saturate the bound. Okay. And what we see is that if we can saturate the bound, okay, if these states Pi, Pj are orthonormal and Qi, Qj are orthonormal. Now let me remind you what the definition of Pi. Now I make another claim that this is true if MIAA gives an isometry from and similarly for n. But let me first explain this, what it means. Okay. What is the meaning of MIAA gives an isometry from this? So let me go back to this figure again. Okay, see this figure. So M has these 3 indices, right? I labels the Hilbert space basis here. Okay. A labels the Hilbert space basis here, and small a represents the Hilbert space basis on the boundary. Okay. At this stage, this is just some tensor with various levels. Now we can think of this in various ways, right? you can think of some of them as input legs and some of them as output legs, and think of this as a matrix. Okay. In this description, it's not a matrix, it's just a tensor with all legs labeled in the same way. So what is the claim? That if, so let's suppose that we think of this as a map from the Hilbert space, from the product Hilbert space of the bulk indices, okay, and the link indices, okay, into the boundary. Okay, the boundary indices on P prime. We can think of it that way. Okay. And if, when you think of it that way, if it describes an isometry, then the claim is that the states Pi are orthonormal. Is this point clear? Any question? Okay, so let me try to explain how the proof goes. So we considered the I think I got disconnected for a while. Can you hear me?
Yes.
Yes.
Okay, I don't know when, how far when I got disconnected. I tried.
Yeah, you're explaining about when small a and the length and the bulk and this. So the boundary map is an isometry, then Pi will be orthonormal. You stop there.
Okay. So this diagram I showed, right? Or I explained
Yes.
something based on this diagram that.
Yeah,
so
you were explaining about it.
Yeah. So the point is that in this diagram, right, that MIA is defined as just a tensor, okay, without any matrix interpretation. But we can give it a matrix interpretation by thinking of some of these as row index, some of these as column index, right? Or some of them as input index, some of them as output index. And so what I'm saying is that let's suppose that we think of I and A as input index. Okay, so what are I level the Hilbert space states here, and A level the Hilbert space states in the bulk, the capital A, and small a is the Hilbert space states on the boundary. So if we think of M as a matrix in that way, okay, namely the I and capital A are the input index and small a is the output index. And with that interpretation, if it happens to be an isometry, then the claim is that the PIs are orthonormal. So I'll try to prove why this is the case, but the meaning of this statement should become clear, right? That what we mean by M being an isometry, okay, it's an isometry when you think of I and A as input and small a as output. Yes.
So what, like what we are talking about right now, the entropy, that is just the entropy of the subspace of the in the logical space, right?
No, on in the physical space.
Yeah, but we are not talking about arbitrary density matrix on the P prime. We are just talking about the representatives of the maps of capital AB to some small ab.
Yes, indeed, that's right.
And that is why we are getting this small NC, 2 to the power NC as the rank of a generic density matrix in this representative subspace. But in general, an arbitrary density matrix will have a higher entropy.
Yeah, see, an arbitrary density matrix, of course, the entropy is not called, depends on what state you are considering, right? So when you're talking, so Ryu-Takayanagi formula refers to the vacuum in the bulk.
Yeah, so what we are trying to say is that within this subspace, which actually encodes the information of the logical qubits inside in the bulk, that is the maximum entropy. This
So it's more than that.
NC log 2.
More than that. We have assumed here that the bulk state that we are considering is a product state on each of the logical qubits, right?
Yeah.
Because you have taken this state as a product of P and Q, right?
Yeah. Yeah.
And we are extremizing with respect to cuts. That means for every such division, it will be a product state.
Yeah.
So assuming that the bulk state you start with a product state, and then you construct its corresponding image in the boundary. For that state on the boundary, we are calculating the entanglement entropy by tracing out the degrees of freedom in Q prime. So Ryu-Takayanagi formula refers to a particular state in the bulk, right? It
I mean, the
corresponds to
formula, I mean, I personally, I'm not sure because the formula is a general one, right? Not
no.
an arbitrary boundary.
No. That cannot be, right? Because how can you get a formula for the entanglement entropy on the boundary that doesn't depend on anything, right? That will obviously depend on what state in the boundary you are considering. So the Ryu-Takayanagi formula, that way I have stated it, refers to the vacuum in the bulk. When the bulk degrees of freedom are in the vacuum,
Yeah.
then that formula is the correct one. If there is a black hole sitting inside the bulk,
Yes.
the bulk geometry will be different, right? The Ryu-Takayanagi formula will give a different answer.
I mean, but we'll still apply it, right?
We'll still
In the
apply it,
sense,
but
like that boundary will also be different in the sense that the states we discuss in the boundary.
no,
will
they will
also
not be
change.
different. They will not be different because boundaries is the same. The same boundary states encode all the different states in the bulk.
Yeah, that is fine. But different states in the boundary have different entanglement, have different entropy.
Yes. Which means that if you take different states in the bulk, right, their image in the boundary will have different entanglement entropy.
Exactly. And the RT formula like relates arbitrary boundary that we can construct on the arbitrary surface we can construct on the boundary to an inner surface, in a bulk a surface in the bulk.
Yes.
Right. Which minimizes the area also.
Yes. But that surface in the bulk can change, can depend on what bulk geometry you are considering, right? We discussed only bulk vacuum geometry. And this picture that I have given is also for the bulk vacuum. Okay, in fact, we'll see that it's not quite the bulk vacuum because you have taken the bulk state to be a product state.
Yeah.
Given that you have a product state in the bulk, we are trying to calculate the entropy of the boundary state, and that's what will give some analog of the Ryu-Takayanagi formula.
Yeah.
And later on, we will see what happens if we introduce entanglement in the bulk, for example, right? Which is a more accurate representation of the vacuum state in the bulk.
Okay.
So there will be corrections to the Ryu-Takayanagi formula, right, that we will study. Okay, so let me say this. So I think that is the meaning of the statement should be clear. Now, what I was going to say is that let's consider the state okay, so this is a fixed state. Okay, let me give it a name, right? Some p tilde is a fixed state of the on the logical qubits in the bulk. So if we take I and J, right, these are obviously orthonormal, right? So I times p tilde and J times p tilde are orthonormal. Now let's see what it maps to. If we think of this as isometry, okay, under this isometry, what bulk state does it, boundary state does it map to? So it will map to M I A times P. So I times A will basically map to I A, and then of course you have PA. Sorry, I should have. Let me go back one step. So this state gets, okay, I times A this is mapped to M I A times A. Okay, that's the meaning of this is the isometry that this generates. If you think of I and A as input leg and A as the output leg. So then I times this state this will get mapped to M I A. That's exactly this state, right? Okay, so I times P tilde then gets mapped to, sorry, this is, let me, so I times P tilde is getting mapped to the state Pi. Okay, so this is a state that is supported on the product Hilbert space of the links, of the cut links and the bulk. Okay. This one is supported on the boundary. Okay, and the MIAA is the isometry that takes it from here to here. Okay. Since these states are orthonormal, right? These are orthonormal. That means Pi and Pj will be orthonormal. Okay, because this is an isometry. Okay, as long as M is an isometry, then Pi, Pj are orthonormal. So this implies that Pi, Pj is proportional to delta Ij. Is this logic clear? So the logic again, let me explain. That we assume that M is an isometry from the indices small I and capital A to the index small a. Then just by the definition, what you showed is that I times P tilde, this state gets mapped to the state Pi in the boundary. And similarly, J times P tilde will get mapped to the state Pj. These states are orthonormal, okay, because P tilde of course has a unit norm and then I and J are orthonormal basis. So the input states are orthonormal by construction. And because M is an isometry, the output states must also be orthonormal. And that's the logic that shows that Pi Pj is proportional to delta Ij. Similarly, Qi Qj is proportional to delta Ij if N IBB is an isometry from IB to B. Okay. So next time we will see to what extent this is true. Okay, whether M and N are both isometries for the minimal length cut. Okay. But today, let me finish by describing an immediate consequence of this. So let's suppose that this is true. Now it's clear that this can only happen for the minimal length cut, right? Because if it happened for any other cut, then the equality is established. On the other hand, we know that there is an upper bound which is set by the minimal length cut. Okay, so clearly there will be a contradiction. So M and N can be both isometries only for the minimal length cut, but the statement is not reversible, right? For every minimal length cut, it need not be that M and N are isometries. Okay, that is something that you have to test. But let's suppose that this is true. Okay, let's suppose that M and N are isometries, okay, and see what its consequences are. So this is P, this is Q. This is P prime, this is Q prime. So if M is an isometry, then that means there is a that you can map states from the Hilbert product Hilbert space of the bulk inputs, bulk states, and the link states into the boundary, right? And that is an isomorphism. And that means that any operator that acts on the subspace on the input can be pushed to the boundary. So this has the immediate consequence that the bulk operators in P can be pushed to P prime, and bulk operators in Q can be pushed to Q prime. And this is the analog of something we had already seen earlier, right? In the geometric from a geometric consideration, that we defined, if you remember, the causal wedge, right? And we are looking at the t equal to 0 slice of the causal wedge. And the causal wedge actually, this surface, okay, as we said, coincides with the entanglement wedge, as long as this is a simply connected region. Okay, as long as the P prime and Q prime has only one connected component, the causal wedge and the entanglement wedges are the same. Okay. So this geometric fact that we had seen earlier, that the region of the bulk, okay, that is in the causal wedge of P prime, is actually mappable to P prime. Okay. And then region of the bulk that is in the causal wedge of this region is mappable to Q prime. So this geometric fact that we had studied earlier becomes automatic, okay, from this viewpoint, from the map that you have described, from this holographic code, but provided, of course, this the M and N happen to be isometries, and that means, so if N and if M and N happen to be isometries, then both RT formula holds, and this map from the causal wedge, the boundary, that formula also holds automatically. So I think I'm going to stop here, and next time we will see to what extent we can actually prove this, okay, that M and N are actually isometries. Okay, I have not so far said whether they are or not, okay, but I have said that if they happen to be isometries, then both the RT formula holds, and then this mapping from the causal edge to the boundary, that formula also holds. Okay, so I think I'm going to stop here. Other questions?
One question.
Yes.
So prior to using the fact that when even in isometry use are orthonormal, when you just found the inequality relation,
Yes.
there the fact that we were using ADS-CF2 was encoded in the definition of the small AB, capital AB inner product.
No, it was
defined as
definition
sum
in the
over I
holographic code. Yeah, exactly. I mean, the fact that we are
Yeah.
defining the bulk to boundary map by
Yeah.
this, yeah,
sum over I mi
exactly.
A,
Yeah.
yeah, because you didn't use any property of mn there, so I thought.
Well, the point is, we had defined this as a product of tensors with internal indices contracted, right? The product of perfect tensors.
Right.
M and
Right.
N are also defined by product of perfect tensors with the internal indices contracted, except that the I is not contracted, right? That's why you have the sum over I here.
Oh, okay.
So both uses the same, both use the same perfect tensors, right? Same products.
Okay.
Other questions?
Sir, I had a general physics question.
Okay, but maybe before you ask a general physics question, we can see if somebody else has question on specifically on this or on these lectures, because otherwise I'll stop recording and then ask a general physics question.
Naively, should we not expect that if the bulk, the bulk state in P and Q are product states, then even the boundaries be product states?
Yeah, but it is not, right?
Yeah.
And that's because of the entanglement across the link.
Yeah, that's what I don't understand. I mean, how is entanglement generated on the boundary if it was not, if the bulk states were not entangled?
Because it's through the holographic map, right? The way we map the states from the bulk to the boundary, right? That's what the entanglement is generated. But it's not that we are directly using identity map from bulk to boundary, right?
Yeah.
So that I mean,
Okay.
it's the entanglement across the
whole,
same C, right?
Yeah,
That's
the whole boundary was constructed using the states at both P and Q and not only one of them.
exactly, yeah.
Yeah. Okay.
Yeah, because when we constructed this, right, we also had the sum over I, right? This in this map, right, included the sum over the links also, right?
Yeah.
Yeah, so that's the surprising fact that even if the bulk state is a product state, the boundary has entanglement. And we will see later that if the bulk state is entangled, then that basically gets added to the Ryu-Takayanagi formula.
Okay.
Any other question on this? Okay, so let me stop sharing and then I'll switch off the recording.